So hello everyone, welcome back to another particular lecture of our asymmetric synthesis course, and this is lecture 2. So in our previous discussion we talk about that what is the importance of asymmetric synthesis, how it is emerged, and what actually motivates the researcher to do asymmetric synthesis. Means the important and significance we are already discussed. That means we have completed the foundation. Now before entering the asymmetric synthesis in details, there are certain stereochemical models that exist which actually help us to predict that which diastereomer will form as a major one. And honestly, from these stereochemical models, there are n number of questions has been asked in that particular competitive examination, such as JAM, NET, or CSIR GATE, and so that's why this particular lecture is very important. Now in the literature there is many kind of stereochemical models are there, such as Cram model, Cram chelate model, Cram and then there are Felkin Ahn model, Zimmerman Traxler model, Ireland model. There are so many models are there, but to our simplicity in this particular class we mainly talk about Cram model as well as the Felkin Ahn model. Let us first understood that what is the stereochemical model. As I already discussed, a stereochemical model describes the three-dimensional spatial arrangement of atom in a molecule to predict stereoselectivity and chemical reactions. Mainly, if you have a carbonyl compound which attached with a chiral center, so when you are adding a nucleophilic attack on the carbonyl carbon, because carbonyl carbon is electrophilic, now then only it can make a new diastereomer. And to predict that particular diastereomer, that how the nucleophile attacks will favor, that actually can be described by the stereochemical models. Now in this particular class we talk about two different models. One is the Cram model and one is the Felkin Ahn model. Now in Cram model there is a three different models there. One is the normal Cram model, one is the Cram chelate model, and one is the Cram dipolar model. So in this particular class we will discuss this all four models elaborately. First let us talk about normal Cram model. So the Cram model are actually been used to predict the stereochemistry while the nucleophilic addition of carbon oxygen double bond. That means you have a carbonyl compound here. Okay, this group and this may be H, and you do a nucleophilic substitution. Now you have to want to predict that what will be the stereochemistry of O as well as the stereochemistry of Nu. And this particular stereochemistry is highly dependent upon that how the orientation of this particular group is there, because this is a chiral compound, so it also have the three different groups, and depending upon the orientation of three dependent group, this particular uh, like nucleophilic addition, like it will act from the upper side or on the below of the plane side, that will determine, that will discuss in the with the example obviously. Now this Cram model are actually predicts the major diastereomer formed during nucleophilic addition to a carbonyl adjacent to the chiral center. Now let's see with this particular example. Okay, but before that, you have to know that the largest substituent on the chiral center is positioned away from the carbonyl group, guiding the nucleophile approach from the least hindered side. That means you have certain a carbonyl compound here, and here is a chiral center which contains one large group, one middle group, medium group, and also small group. And this is the chiral center. Now, this particular position of this L group are actually very important to determine the stereochemistry, because in this particular model it has been said that when your compound is something like that, the large group are positioned away from the carbonyl group. That means the angle between large group and the carbonyl oxygen group is 180 degree. That is clearly shown in the Newman projection formula. And depending upon the nucleophile, it will follow A route or B route. That completely depends. Okay, when it is formed the A route, then this particular enantiomer is major. Over when this is follow the B route, then this is minor enantiomer, or this is major. Now how the nucleophile will choose to where to attack, that we will discuss in the with the example. For example, this is your compound, okay, and you have to treat this particular compound with lithium aluminum hydride, which is nothing but a hydride donor to the carbonyl carbon. Now you in the question paper it has been asked that what will be the major product here, means what is the stereochemistry of OH, predict that stereochemistry via Cram model. So first we have to draw this in a Newman condition, so that we have to prepare a circle, okay, and always remember that the viewing angle would be from this carbon only. So the front carbon contains the carbonyl as well as the methyl group. Now you have to check that how this particular carbon is been positioned. So the simple and easy answer is draw a line here, okay, and you can see that particular H is present in the right side of that particular virtual line. That means this is when we are viewing this angle. Now since we are viewing from this angle, so obviously that I am really sorry, okay, so that pH and O are in a eclipsing position, so we put the pH here, and as you know that this H is present in the right hand side, but we are viewing from this side, so it will be go here, and this Me is initially present in the left hand side, but we are viewing from the opposite side, the mirror side of this particular, so it goes here. Now as per the Cram model, we have to rotate that particular bond such a way that the angle between the pH, that is the large group here, this is the medium group and this is the small group. The large group pH will have exact 180 degrees, the staggered position of the carbonyl carbon. So we just rotate such a way, okay. So we got this our carbonyl CH3. We got pH here. It goes here, so that means that methyl will go here, as well as the H will go here. Now your hydride will attack. Now that particular hydride have two possibility. One, it will attack from this side, and one, I just changed the pen color, one it can attack from the this side. Now if it follows the red pathway, if red pathway follows, then it will face significant steric hindrance because methyl group is there and the O is there. However, if it follow the blue one, then it will face lesser steric repulsion. That means this particular attack, the blue color attack, is favored. So the final product will be, the back carbon will keep intact, this will here methyl. Now since this is attack from this side, so OH will push out to the methyl side, OH, and this will come H. Now we have to make this again in the staggered position because it is again eclipsing, okay, or we can keep like that way also, for example that, but since we have to back that particular geometry, so we have to rotate such a way. So this is the OH here right now, this is the H, and this is the Me. So the pH will back here, okay, the Me will back here, and H will back here. So this H is Nu. Now the interesting observation is here that when these are like that way, like we just make this particular bond, so remember that these two group as well as these two group have same stereochemistry, that this have same stereo, this also have same stereo. That means now if we draw that particular compound, then we will find that pH, this is our backbone, that PHMe. Okay, now this particular OH is the this particular carbon. I just highlight it with another color, this sky color. So this and this have the same. So in the backward case, the H and OH stereochemistry is same. So that means the stereochemistry of OH is this, and so that H. Similarly, methyl in the back carbon, this is contains the above the plane stereochemistry, and as well as the H here, that is which is the nucleophile from the lithium aluminum hydride. This also have OH stereo. So that's how you have to approach that particular questions. Okay, so I just simply rub it off everything and show you through the schematic diagram. Now, as I already discussed, that we have drawn this particular structure. Now we draw that particular structure initially. So here initially that O or pH in a eclipsing position, as the diagram says here. Okay, now we have to rotate in such a way, then these two will observe, that I already discussed, that methyl will go there and H will go there. After that, the hydride attack happens from the lower hindered side, because this will blocked by the steric hindrance. So it will form this particular as a major one, followed by we rotate to bring back our initial conformation, just like that. And after that, these two and these two will have same share the same stereochemistry. So this product is the major one. So that's how you have to approach that particular Cram's model questions. Okay, and also there is a short formula is also there, which only apply for the normal Cram model. The formula is like this. Formula will help you to cross check in your exam that you are doing correct or not. So the short formula is, when the large group, this is, and the carbonyl both are in the same side, that means in the eclipsing position. Okay, then always remember that the nucleophile stereo will always possess the medium group stereo when large group and the carbonyl are in eclipsing position. If large group and carbonyl group in the opposite side, that means a staggered position 180-degree apart, then the nucleophile stereo is equal to small group stereo. This is the very important short trick, and this actually saves you in the examination. Now let's move to the variation of Cram model, that is called the Cram chelate model. Cram chelate model says, when a carbonyl compound has a coordinating group in the alpha position, that is the has a coordinating group like a alcohol and amine, it can form a chelate with the metal ion, such as Mg2 plus zinc 2 plus NaBH4, a Luce reagent, okay, Gilman reagent, etc. That means, for example, here the all are phenyl so they are not chelating, but any of that particular group is either OCH3 or NH2, then this normal Cram model won't work. So at that time you have to make your transition state such a way that your carbonyl group as well as the chelating group both are in a eclipsing position, and the driving force is both are chelate with the metal ion. Such suppose you are reacting your this type of carbonyl compound with a Grignard reaction. Now this particular Mg is allowed to chelate further, so this particular orientation of that particular molecule will become more favored because of the chelation effect, and from there this particular R will now attack from the lesser hindered side, and it will form this particular intermediate, and after getting the correct Newman formula, we'll get the final product. In that particular case, it's not necessary to put the carbonyl oxygen as well as the large group in 180-degree apart, but you have to make sure that the chelating group and carbonyl compound has the closer proximity to allow us to chelate. For example, here also you can find the similar type of structure but a different orientation, so this will also lead to this type of product. And remember that this type of Cram chelate model will not are entitled into that particular short formula. This short formula only applied to the normal Cram model. Now let's talk about another particular variation of Cram model, that is the Cram dipolar model. This Cram dipolar model only applies when a strong electronegative group or halogen is present at the alpha position of the carbonyl group of the reactant. Means when your compound contains this alpha position that contains a chiral center, okay, is a large group, small group, and X is the halogen. Then what happen, you have to draw your transition state such a way that the carbonyl oxygen and the halogen group should present in the 180-degree apart to eliminate the dipolar repulsion. Okay, to minimize the dipolar repulsion, the two group must anti to each other, and this will be your starting Newman projection. And from there, you have to check the nucleophile attack. Now, if the nucleophile attack from the less hindered side as well to form this type of product. And here also in Cram dipolar model, here also it is not necessarily to put the large group in the anti. It might happen that if that particular is chlorine, and this is a large and here is methyl and here is hydrogen, that means your large group is equal to halogen, so that time it works as a normal Cram model. But if not, that if it is that pH or something, then it will not act like that way, so you have to put the halogen always anti to the carbonyl oxygen. So this is the Cram dipolar model. Now let us talk about Felkin Ahn model in details. So now let us talk about Felkin Ahn model. Felkin from the Cram model, Cram chelate model, and Cram dipolar model, because in Felkin Ahn model, basically it has been proposed that in the case of carbonyl compound, the particular nucleophile attacks in the Burki-Dunich trajectory. That means, so suppose this is your carbonyl compound. Now the nucleophile attacks here at the angle of 107 degree. This is called the Burki-Dunich trajectory. This is because that the pi orbital present here is allowed to attack from this way. So to show this particular in a model, they have shown something like this, where the large group and the carbonyl group, the angle between large group and the carbonyl group is nearly 90 degree to show the Burki-Dunich trajectory here. So if we just convert this into Newman projection formula, then what we find that we have to see this particular compound from this side. So we just draw the OCH3 part here. Now the L part is anti to each other, so L will be here. Now between these two, where the middle group and the small group is there. Okay, now you can remember that, draw a imaginary line here. Now between this imaginary line, you have to see that the M group is present in the right side of this particular imaginary line. That means when we see from this particular group from that side, that will be on the left side. So M will be here. Similarly for the case of S, it will be here. This is a short trick. You have to remember this to make this particular making this model easy. Okay. Now if we just rotate it to maintain the large group between the angle between the large group and the carbonyl group is 90 degree. So we can find here, this will be keep here OCH3. If we rotate here like that way, that means L is here, M is here, AC is here. So this, we got this particular intermediate, and here you can see the steric angle is lesser compared to if we rotate in that fashion. If we rotate this fashion, then we ended up this intermediate where the methyl group as well as the medium group are in a closer proximity. So that's why there is a higher chance of repulsion, steric repulsion here over this. So that's why this particular intermediate is preferred intermediate over these two, and followed by after attacking we got this particular as a major isomer over this, which is a minor isomer. So this model you have to remember, this is very important for your exam point of view. And with this we have to end this particular class. In this particular class we discuss about Cram model in details, Cram chelate model, Cram dipolar model, as well as the Felkin Ahn model. So in the next class onwards we enter into the asymmetric synthesis part, the actual asymmetric synthesis. So I hope that you will learn something from this particular class, and this particular class is very important for your competitive exam. So if you have any difficulties, you always go back to the video and check, and while you are doing some question regarding this concept, that particular concept getting more clearer and clearer. So with this we have to end this particular lecture. So thank you for listening.